Good day and welcome. My name is David Purcell. I'm a business development manager here at FLIR Systems, and it's my pleasure to present this webinar on behalf of FLIR. I appreciate you taking time out of your schedules today to meet with me for the next 30 to 40 minutes discussing the key differences between thermocouples and infrared cameras for temperature measurement. The agenda for today's webinar is as follows. First, I will share a real-life example of a company that uses both thermocouples and infrared cameras for conducting temperature measurement. I will then follow with a review of how we currently measure temperature with various measurement technologies that are available today. I will then explain the basics of how thermocouples and infrared cameras work. Following this, I will conduct an experiment using both thermocouples and an infrared camera to measure temperature. And I will conclude by reviewing the results of that experiment. So let's get started. We recently received a phone call here at FLIR from one of our refinery customers. Now, this particular customer, they had purchased a portable handheld camera for imaging and conducting thermal analysis, temperature measurement of their furnace tubes. And the individual who was trained and tasked with making the tube measurements, he discovered some measurement discrepancies between his infrared camera and 4 permanently installed thermocouples within one of his furnaces. In fact, what he discovered is that the thermocouples, they were reading about 750 degrees Fahrenheit, while his camera was indicating 1,300 degrees Fahrenheit. Now, based upon the melting point of furnace tube materials, this particular thermographer went into alarm mode, and he warned his management there at the refinery that they needed to shut down that furnace before it failed. Unfortunately, though, his management believed the thermocouple readings over his camera measurements. What resulted was the furnace burned down and resulted in an over $20 million loss for this refinery. Now, eventually the furnace was rebuilt and the refinery started back up. And during the commissioning phase of the furnace, this same thermographer, this technician, he realized that the thermocouples indicated about 750 degrees Fahrenheit. Yet his camera, it indicated about 850 degrees Fahrenheit. So the difference wasn't off too much, but he decided he would continue to monitor closely. Now, 2 months later, the thermocouples were still reading 750 degrees Fahrenheit, but his camera was now measuring 1,350 degrees Fahrenheit. So what do you think happened? Well, this plant thermographer became a little suspicious about the varied readings, and he decided to contact us at FLIR. And we at FLIR, we wondered, first of all, about the calibration of his camera. Was it in calibration and was it reading accurately? So we decided we would send him one of our demo cameras. We would loan him one of our cameras so he could perform a measurement check. He could compare his camera against our demo camera, which we knew was calibrated and measuring correctly. The results of his comparison indicated that both his camera, the plant camera, and our demo camera were measuring the same. They were both measuring 1,350 degrees Fahrenheit on these particular tubes. Now, using this backup information, this thermographer was able to convince plant management that they needed to increase the flow rate through these tubes. And by doing so, they would reduce the temperature of these tubes. And they took his recommendation. The tubes did in fact cool, and that action, it definitely averted another crisis there at this refinery. So during the next plant shutdown or turnaround, he decided to do a closer examination of the thermocouple measurement system, and what it revealed was that the system was way out of calibration. So this thermographer and his camera now definitely have more credibility within the eyes of plant management there at the refinery. So in summary, The management at this refinery assumed that thermocouple measurement there at their facility was the truth, and they did not necessarily trust the IR camera results. This assumption resulted in equipment failure, equipment replacement, and an unscheduled plant shutdown. This assumption cost this company time, resources, and money. Now, seeing the potential devastating impacts of inaccurate temperature measurement, let's briefly review what it really means to measure temperature. First of all, I'll ask the question, do you realize there is no direct method to measure absolute temperature? There is no direct method. All temperature measuring devices, they report a temperature value by measuring an effect of temperature or an effect of heating and cooling. For example, a thermistor, it measures changes in resistance associated with changes in temperature. A thermometer, it measures a change in volume associated with changes in temperature. A thermocouple measures changes in voltage associated with changes in temperature. And an infrared camera, it measures changes in infrared radiation associated with changes in temperature. All of these instruments report a temperature value based upon the measurement of some other parameter. For today's presentation, I'm going to focus on just two of these measurement devices. I'm going to focus on thermocouples and infrared cameras. By way of history, it was Thomas Seebeck who is credited with the discovery of the thermocouple, and he did this in 1821. What he discovered was that when a conductor is subjected to a thermal gradient, that conductor will generate a voltage. Now, this effect is known as the thermoelectric effect, or Peltier-Seebeck effect. Now, the science behind creating a thermocouple is actually quite simple. I have an illustration here that shows a thermocouple measurement system. If we take two conductors of two different materials, in this example, in my illustration, I have metal A and metal B, and I expose them to the same heat source, we will get two different induced conductor voltages. I will have a voltage in metal A, and I will have a voltage produced in metal B, and they will be different. Now, if I can measure these differences in voltage created by these conductors for various temperatures, I can then calibrate the system. And if I can calibrate it, then a given temperature input will produce a specific voltage output. And now when I know this temperature to voltage relationship, it will allow me to determine a temperature value for unknown temperature sources from measuring voltage. Now, in my thermocouple circuit here, you may have noticed a third metal connected to our conductors. This is metal C in our illustration. This third metal connects conductor A, or metal A, and metal B to our voltage meter. Now, you may have realized that these two additional junctions, and that's the junction created at metal C to metal A and metal C to metal B, that I've essentially created two new thermocouples. As such, it's critical to maintain these two junctions, highlighted here in my illustration, at the same temperature so as not to introduce additional voltage that could have an effect on my voltage output and skew my readings. So it's important for me to control the temperature at these two junctions. In my example here, I have what's called the cold junction, and the cold junction represents this entire area, the junction at A to C and B to C. Now, if I control that temperature there, I will not introduce any additional voltage into my thermocouple system, and now I'll be able to accurately measure the voltage at the hot point, or the point of interest. Now, there's an additional benefit to having this cold junction, and that is that if I know the temperature at the junction, it provides me a reference, and that reference will allow me to determine the actual temperature now at the measurement junction, my point of interest. Now let's look at the operation of an infrared camera. In this example, I am referencing a FLIR T420, and this camera, it has an uncooled microbolometer focal plane array infrared detector. Now, a microbolometer is a thermal-based sensor, and what that means is that the sensor produces a resistance change when heated. Now, the focal plane array in my camera, it contains 320 by 240 over 76,000 detector elements. Each one of those detector elements is a single bolometer. Now, with the lens of the camera, I can focus infrared radiation onto the detector elements. As that radiation, infrared radiation, strikes those elements, they heat up, and their respective resistance changes. Now, using what's called a readout integrated circuit, we can measure the resistance change for each element and convert the reading to a digital count. Most infrared cameras digitize at 14 bits or 2 to the 14th power. This digitized data coming from each of those elements is then calibrated to a temperature. It's assigned a color or a grayscale value and presented as an image. Now, because our image is made up of individual detector element measurements, we can use analysis tools to highlight specific elements and display their respective values. I can use an area tool to display the maximum, minimum, or average temperature within an area. I can use spot tools to display the temperature values from any element within my image. Making measurements with an infrared camera is like having over 76,000 spot pyrometers in the palm of your hand, making measurements simultaneously. Or you can think of it like having over 76,000 thermocouples taking temperature measurement or reporting temperature measurement from your target of interest. In summary, the two temperature measurement technologies I am speaking of in this webinar, thermocouples and infrared cameras, neither of which measure temperature. They measure an effective temperature. The thermocouple, it measures changes in voltage caused by heat, and the infrared camera measures changes in resistance caused by heat. Both of these instruments calculate temperature outputs based upon their respective unit of measurement. So let's compare these two measurement technologies by conducting a simple experiment. I will fix a thermocouple to the inside and outside of a can at the same location, and then I'll fill the can with hot water. I will then take measurements with the thermocouple and infrared camera and compare the results. For our experiment, I am going to use an X-Tech EA10 dual input thermocouple. This is a type K thermocouple, and there are other types of thermocouples available, such as EJN, BR, S, T, and M. Now, each type of thermocouple is made up of a different metal combination. They have various sensitivities, measurement ranges, and they vary in cost. The type K that I'm going to be using is the most common, general purpose thermocouple. It has relatively good sensitivity and it's relatively inexpensive. This is an image from our infrared camera of the thermocouple attached to our can filled with hot water. What can we determine from this image? Well, first of all, the image temperature scale located on the right side of our image indicates the color-temperature relationship or distribution. The maximum temperature display corresponds to the lighter colors in our image, and the minimum temperature display corresponds to the darker colors in our image. Now, from this color display, we can see that a temperature gradient has been established along our thermocouple leads. Now, what does this image tell us about the thermocouple reading the surface temperature? The large rectangular area in this image is a piece of black Scotch 88 electrical tape with an emissivity of 0.95, thus meaning 95% emission comes from the tape. Now, this tape is a great emitter of infrared radiation. Assuming that the tape now has reached temperature equilibrium with our can surface, the color temperature of the tape is a good indicator of the can surface temperature. From the image, we can see it is relatively uniform in color, indicating relatively uniform apparent temperature across the area, the tape area. If the thermocouple is reading close to surface temperature, what color should it appear? Now, shouldn't it be the same color as our tape? Yet the infrared image indicates it is slightly less. So let's look at our experiment from a visible perspective. T1 is the outside thermocouple, and it is reporting a temperature measurement of 99.1 degrees Fahrenheit. And T2 is the thermocouple that is placed just inside our can at the same point, and it is reporting a temperature measurement of 114.1 degrees Fahrenheit. Now, clearly, these two readings don't match. But why? Well, let's explore the possible causes for inaccurate thermocouple measurement. First, our thermocouples, they do not exist in isolated environments. They are subject to not only conduction effects, but they are also impacted by radiation and convection. The images displayed here were taken with a very sensitive infrared camera. The variation in the grayscale display indicates subtle temperature variations caused by natural convection occurring at the surface of our warm can. Now, while the effects of natural convection certainly impact our thermocouple temperature measurement, contributing an approximate 1 degree variance, it does not explain the large 14-degree difference from the internal thermocouple measurement to the outside thermocouple measurement. So let's take a closer look at our experiment setup and the components in our experiment to see if we can find other possible causes for the error. Now, thermocouples are typically very small, and intuition says that if the mass of the surface is very large compared to the thermocouple, that heat transfer from the surface to the thermocouple will be adequate for measurement. However, I should note that all temperature contact sensors require appropriate mounting so that they achieve the same temperature as the surface to which they are in contact. Considering the geometries of our curved can surface and our spherical bead thermocouple, we should ask, do we have sufficient contact for adequate heat transfer to occur? My gut is telling me we do not. However, additional testing should confirm this for us. So let's repeat our experiment with the introduction of a permanently mounted thermocouple. In this example, I am using an Omega CO1 Type K fast response thermocouple. This permanent thermocouple is cemented to our can surface with a high temperature, high thermal conductivity cement that requires a 9-hour cure time at a high temperature. Now, please note, any cement used to attach a permanent thermocouple must be thin, conductive, and present the least thermal resistance as possible. So after refilling our can with hot water, the qualitative IR picture tells us that the cemented thermocouple on the left is at or near the same temperature of our surface, while the temporary fixed bead wire thermocouple on the right clearly is not. Looking at our redo or do-over experiment from a visible perspective confirms our thermal image qualitative assessment. That is, the permanent inside thermocouple and permanent outside thermocouple measurements are within 1 degree, while the removable outside thermocouple is off by more than 17 degrees. The chart I'm displaying here compares the measurement results from all our measurement instruments. In general, the cemented or permanent thermocouple and infrared camera produced fairly accurate results, while the bead wire or removable thermocouple results were unreliable. These results confirm our original assessment of the temporary mount or bead wire thermocouple. We clearly are not making the necessary contact with our surface for adequate heat transfer to occur and for accurate temperature measurement to result. So, in closing, let's review the results of our experiment and what we have learned about thermocouples compared to infrared cameras for temperature measurement. First of all, we learned that temporarily installed bead wire thermocouples, while they're inexpensive and most generally the most generally used thermocouple, they do not make very good surface temperature measurements. It is very difficult to get good heat transfer between the target surface and the thermocouple. Second, we learned that permanent or cemented thermocouples give very good surface temperature measurement. However, they require a fixed mounting, making them non-transferable. Additionally, they are adhered with a cement that requires high temperature exposure and long cure times. Using this type of thermocouple could create complexity if a target requires multiple point measurements. Finally, we learned the results from the infrared camera are fairly accurate for surface temperature measurement. Additionally, the camera images are very easy to interpret. And with the infrared camera, we can extract measurement values from several thousand locations. It is important to know the emissivity of your target, though, to get good, accurate temperature measurement. Again, thank you so much for taking time out of your schedules today to meet with us as we discussed the variances and differences between thermocouple measurement and infrared camera measurement. I hope you enjoyed this webinar. I'd like to open it now for question and answer. Thank you.